welcome and nice to meet you again. Looking forward to the course. After discussion with um, Samir, I will present. You've seen the three topics in the agenda, of course, but it will be a bit different from the format last time. It will be a little bit more hands-on. I don't want to say interactive. If we had the pleasure to be in the same room, I would actually do it interactively. So have distributed some scripts for you, and we could look at them together. But um, it will be one way I'll be doing it, so not interactive, but it will be not only presentation. It will be going a bit back and forth. So first step will be that we need to figure out how I can share my screen properly, such that I can um, move between the different items. So I'm intentionally not sharing only the presentation, but also my screen, right? You can now see the Visual Studio coding environment, and now you can see the presentation. Is that correct?
Yes.
Yes. Okay, good. Then I think we are all set. And I go ahead. So the HD user training second level and boundary conditions, or I should actually have said boundary conditions and forcing will be covered. So input to the HD model. And the agenda for the next session is, the first one is that we do a quick recap. So there will actually be a little presentation part, a quick recap of the water level variations. That's a few selected slides from the level 1 training that I added here again to just talk through it quickly, because I thought it might be good to recall that before embarking onto these examples. And then I prepared 4 examples: wind setup in a closed lake, wind setup on a coastal profile, then a wind speed event profile, and a water level event profile. And we will go through these example by I prepared some notebooks, some Python scripts to generate the input, to batch generate the model runs. Then I already run the model runs, but then we will also load the results and compare them. And I hope with that it's not high level theory, let's say, but it's some hands-on tools that I hope you will find also useful in maybe understanding the technical work steps that have been in the flood model, and also to apply the flood model moving forward to applications. So I guess as engineers, we need both, right? The theory, but also the hands-on capabilities to actually set up and process these models, especially when it becomes a lot of cases. Then you don't want to be manually opening GUIs and clicking around. So that's the agenda. The recap: water level variations. So there were short-term, seasonal, long-term, and rare extremes. Is one way of sorting them. Long-term is relative sea level rise with land, emergence, and subsidence plus the sea level rise. And sorry, the order was still not correct. And then short-term, we have the regular predictable tides, and then we have a lot of irregular contributions. And I already said different data sources and models will contain the different contributions. And that's what you need to keep in mind when you set up your model. Okay, what of these components, because they all in the real world, they will all have an impact on the water level that you get along your coastline and that you get along your dikes, that will control the flood levels when you're doing a coastal flooding study. But you will, as a modeler, have to decide, well, first of all, which of these are actually relevant and which of these might, be just excluded. And then which of these are handled either on the boundary to your coastal model or which are handled inside the model. And it's not black and white, but that's something you need to figure out. So tides were these regular water levels. We know there's for example, the global tidal model. There's some tidal water level shown here. The global tidal model, that's sort of applicable some distance from the coast in deeper water, and then you can, when you apply a tidal boundary on the regional or coastal HD model, then you will use that model to propagate the tidal wave into shallow water. Along the coast of Egypt, it's actually not such a large contribution, and the variation from the offshore boundary to what you see near the coast is also very minimal. This is more the correct propagation of the tidal wave becomes more relevant when you're looking at estuary systems. So where you have like some critical cross section and you have some complex bathymetries where new constituents might arise, and etc. etc. But it is there, and it's the amplitude is around 20 centimeters along the north coast. So it's not the largest contribution compared to, for example, climate change for your application, but it's there, and we take it in the model because we want to make the model as accurate as possible. The next one was a storm surge. So that's an temporary increase in water level resulting from shear stress by onshore wind. And well, there's this analytical solution here, and this goes from deep water to shallow water. And the more shallow the water gets, the more the contribution to the setup is there. And then this one will be actually, depending on where your model boundary is, this one will be partly included on your boundary and partly resolved inside your domain. Or you could also say, well, I'm only interested in the water level here, so I'm not so interested in what the profile looks like here. So you could say, I just compute that value over here myself and also apply it to the boundary, right? So that's a model choice you could make as a modeler. Then you just know, okay, I actually added this setup due to the wind, the shallow water setup, already on the boundary, meaning that my water levels here will probably not be entirely correct, but here they will be okay. That's not what has been done in the Egyptian model. There we actually have wind forcing, so we reproduce this here inside the model. So that's the more accurate way of doing it. Then there is a barometric surge, so that's sort of due to larger pressure fields moving around in the Mediterranean in your case, and that is, one can say, included in the on the boundary, on the offshore boundary, or on the statistical water level values we actually apply for the flooding, right? We're not modeling hindcast time series, we're modeling some synthetic extreme cases. And then any barometric surge is sort of included in that at the offshore boundary. And then we had the impact of waves, all the different ones. There was a wave setup, the surf beat, the wave uprush, and the wave run up. And basically, relevant for the HD modeling is only the wave setup. So there it can be dealt with, and it was taken with in the ICZM model, and that can be done by either similar to the wind, pre-calculating a wave setup and sort of adding it to the boundary, accepting that we make a small mistake by sort of applying a constant wave setup across the entire domain. Or it could also be done by applying shear stresses from a spectral wave model to the HD model and then computing it inside the HD model. I will get back to that in my last session tomorrow, where I want to cover a little bit of coupling between spectral wave modeling and hydrodynamic modeling. And then the surf beat, that's the oscillation in wave setup caused by wave grouping. That's actually something we cannot reproduce in the HD model because we are looking at statistics, at wave statistics, so the significant wave height over 1 hour, for example, and assume that it's quasi-stationary, so a constant HS over an hour. But you can actually, especially in sort of reef islands where it goes from 6,000 meters to 10 meters, and then you're on a reef and you're exposed to long period swells. So in the Indian Ocean, Pacific Ocean, you can find a few examples. Then these long swell waves actually break, and then they give sort of a small water level up and down at a period of maybe 30 seconds, 1 minute. So that's something that's that's sort of only a phase resolved model can reproduce. But that's again not and we have of course some projects where that is relevant. If that is relevant, you need to think about how you can do that. You could, for example, again estimate the maximum surf speed and apply it as an additional water level at your offshore boundary. That would be sort of the conservative approach, or you need to go for some phase resolved models. And phase resolved, I'm meaning computational fluid dynamics, like Mike 3 or OpenFOAM or whatever. But that's outside of the scope for this session here. So that's just for completion. All these wave-related water level variations are there. Relevant for us in context of the HD 2D coastal modeling is the wave setup. Sea level rise, yeah, we talked about that. So the sea level rises and the land moves up or down. It subsidizes there's a subsidence in Egypt, and then there is a relative sea level rise that's relevant for our scenarios. And then I try to sort of put a bit of an overview of, okay, how do we now deal with these different water level variations in the context of the 2D HD coastal flooding model. So we have the tide that's included on the boundary. It's not really resolved in the model. You could also include the tidal potential in addition inside the model domain, but it's, if you're only modeling 4 kilometers out from the coastline, that's not relevant. If you set up larger domains, then it becomes relevant to also include the tidal potential inside the model. Then the search here, I sort of think of I pointed that out at the profile earlier. The search, it depends on, of course, where your offshore boundary is. But here I'm sort of thinking of a regional search, like an overall search that you have at your offshore boundary. Then that is, of course, included at the boundary. But then there's also shallow water search. So what happens with the additional wind setup when, in more shallow water, and that can be resolved in the model by importing wind speed, and that's what we did in the ICZM model. It could also, and that's why there's the X in brackets, be included on the boundary if pre-calculated. The barometric search, it's included on the boundary because it's included in the extreme value analysis of the water levels. So it's and so is the contribution of climate change. And then the wave setup, it's also included on the boundary for the different wind speeds. Talking of the ICZM model for different wind speeds, the different wave. For the different water level, a different associated wave height is found from joint probability analysis, and for these wave conditions, wave setup is pre-computed, and then for each case, that additional wave setup is added to the boundary, so it's constant across the domain. It could also be resolved in the model by inputting radiation stresses from a wave simulation, and as I mentioned, that's something I have on my list to look at tomorrow. That's slides for here until here, and then I have a few examples. In light of time, I would suggest that we go through the 4 examples one by one and always do questions at the end of
Excuse me, Henrik.
Yes.
Just 1 minute to recap this point in Arabic with Trini. Give me 1 minute or 5 minutes.
Yes.
Okay.
Okay. I use that break for my.
Yes. Enjoy your break. الفكره هنا ان دي اسمها الووتر ليفل فاريشنز والفورسنج تيرمز. يعني انا دلوقتي عندي دومين اهو. الدومين انا عايز احط عليه الفورسنج تيرمز. ايه اللي هيتحرك في الدومين؟ فانا عندي من وجهه نظر الووتر ليفل الميه، فانا عندي باوندريز اللي انت حضرتك شايفها اللي هي داير ما يدور الاوضه دي اسمها باوندري. فانا ممكن احط الووتر ليفل فاريشن على الباوندري بس. يعني اجي على الباوندري هنا اهو وابتدي احرك الباوندري. سجاده، دي سجاده، وانا ماسك طرف السجاده وابتدي احرك طرف السجاده. فاللي هيحصل ان السجاده على مستوى الدومين كله هتتحرك، صح؟ وممكن كمان اخلي الناس تخش جوه، يعني حضراتكم جوه الدومين تحركوا السجاده من جوه نفسها. فاذا انا عندي تو اوبشنز، اما ان انا include it on the boundary او resolve it in the domain. يعني كمان تبقى متاثر بالدومين من جوه. اوكي. فهو بيقول ايه التايب اللي هي حركه الميه نتيجه القمر والشمس والقمر والشمس بتنزل وكده. فدي بنحطها على الباوندري فقط. اوكي. السيرج اللي هو نتيجه الويند فبنحطه برضه على الباوندري فقط. الشالو ووتر سيرج اللي هو تاثير الويند جوه في المنطقه الشالو، المنطقه احنا عندنا ايه؟ الويند بيتاثر بعيد. فاكرين لما كنا بنقول ان سي ويفز وفي الثانيه كان ايه؟ سويل. فالسيرج الويند هتعمل سويل جديد. بس انا الويند بتاعي فرق، فدي هحطها على الجراوند. اوكي. كمثال هنا الشالو ووتر سيرف هنا عندي تو اوبشنز، اما ان احطه على الباوندري او ان انا كمان اكونسيدر في الدومين بتاعي نفسه. لما بحط الويند فورس ده لو انا حطيت الويند از ويند يبقى دلوقتي ايه كمان هي بتتحس جوه الدومين. يعني نتيجه الويند فانا بحسب الفاريشنز جوه الدومين جنريتد من الايه؟ من الويند. البارومتريك اللي هي جايه من البريشر. احيانا لما تكون ستورمز عاليه قوي فبيحصل منخفض جوي ومرتفع جوي. الحاجات دي بتسحب الميه لفوق او بتنزل الميه لتحت. فلما يكون مرتفع ضغط كتير يبقى ضغط الميه تنزل تحت. هو كان مدي اكزامبل في السلايد اللي فاتت ان ده بيوصل اراوند 0.3 متر. يعني ممكن يحصل ممكن يحصل حاجات لو البريشر دروب او البريشر انكريز عالي ممكن يوصل فوق 3 متر. فده الايه؟ البارومتريك سيرش. فده بحطه على الدومين من بره. ان انا عندي ستورم جايه قويه جدا عملت منخفض جوي فرفعت الميه بعيد في ليبيا مثلا. كان في ستورم او حاجه في ليبيا رفعت الميه جامد قوي فانا بحطها على الباوندري بتاعي. اوكي. والويف سيت اب برضه الويف عندنا تو اوبشنز. هو اما انك تحطها الويف سيت اب تحطها على الباوندري تحسبه اناليتيكال الويف سيت اب بتاعك كام. الويف سيت اب في اناليتيكال اكسبريشن اللي هو كان قلنا من شويه معادله. فممكن تقوم حاطط الويف سيت اب مباشره او تحطه في الدومين اللي هو هتعمل انتر اكشن ما بين الويفز اللي هو انك تحل ويفز وهيدروداينامكس مع بعض. يعني احنا حلينا الويفز لوحدها. المره اللي فاتت بنحل الويفز لوحدها وبناخد منها السيت اب نحطه على الهيدروداينامكس او العكس ناخد من الويف من الهيدروداينامكس نحطه على ايه؟ على الويفز ونحل الكومبلكس سيستم. دي اللي هنتعرض له بكره ان شاء الله في السيشن الاخير اللي هو كابل موديلز. والكلايمت تشينج زي السي ليفل رايز والحاجات دي تتحط على الجراوند. اوكي. فهمتوا؟
وانا كده لما اجي اتعامل مع السيشن في الاخر هتعامل معاه كومبوننت واحد مش هعرف اعمل له نفس اللي هو عامله برضه. يعني لما اتحمل السيشن يبقى ووتر ليفل تشينج
كده هحطه از ووتر ليفل تشينج.
يعني لا سيريس ووتر ليفل. انا مش هيبقى فيه الحته اللي انا بقسم السيريس والشالو والبارامتر. هو اتحط كعين مفاهيم.
هو الفكره كلها ان لو انت حطيت الويند، يعني لو انت حطيت الويند فانت دخلت جوه الدومين، يعني دخلت التاثير بتاع السيرش في الدومين، نساله بقى مش مشاكل يعني.
كده لما بدخل السيرش بيبقى انكلود معاه، لو انا دخلت على الداون بيبقى انكلود معاه التايتل.
لا طيب بتجمعها كل ده بتجمعها. ها؟
التوتال بتاع التشينج بتاع
ايوه التايب ده جاي من الاقمار الصناعيه، ودي كونستيتيوتنتس، معادلات ثابته مالهاش دعوه في ويز في ويند ما فيش ويند، دي مالهاش دعوه بالموضوع ده. انما السؤال الاولاني بتقول ان انت ازاي هتعمل سبريت للسيرش للثري كومبوننتس.
اول ما بتخش على باندل وبتخش بقى اوتر ليفل تشينج.
ما هو هنا هيخش اوتر ليفل تشينج. There are one question here. Are you available, Henrik?
Yeah.
There are one question about the search. The search contribution, how you can split the search contribution into three components, which is the search and shallow water search and barometric search on the boundary.
Yeah.
Uh,
So we go quickly back from the English terms you also used in your explanation, Samir. I think you already covered parts of it, but let me then try in my words again. So search is a bit of a wide term, so it can also just be seen if we even go back one more time here. Basically, there's regular water level variations, and then there's irregular water level variation, which is also called the residual or the surge. And then there's a nearshore wave impact. So now we are in the surge box. And then you can sort of think about how do you separate it. The Seiche, which is like a resonance effect, that's irrelevant in the Mediterranean Sea. But then the storm surge and the barometric surge. There's so only two for now. And then we will split this one here into two later. And I'll tell you in a second why. So the storm surge. In theory, it says nothing else but the water level variation due to the wind force on top of the water surface, right? So in the very simple case of this coastal profile here, you have this water level at mean sea level and you have a wind blowing in that direction, then the water level will increase towards the shore. But this is a bit simplified because there is regional effects and local effects. So the local effects is like, let's say if you put your boundary condition here, then this will be all local. But if you put your boundaries condition closer to the shore, you might already have some small contribution. And that contribution can also be, yeah, it's basically regional effects. So any non-tidal water level variation in your regional model that can be because the, yes?
Excuse me, please. There was some issues in the internet in the 2 minutes ago. Please start from this slide again. Storm surge.
Okay. So yeah, maybe just to be sure, this you said so right. We have the regular and we have the irregular. The irregular is sort of the surge, also sometimes termed the surge. So it's a bit of a fluffy term. And within the surge, we have the storm surge, the barometric surge, the Seiche. Seiche is irrelevant. So now we look at the storm surge. And that's basically just the effect of the body of water onto the wind, to the wind forcing. And one effect that is happening is in shallow water that you have that wind setup. Quite, yeah, a significant contribution. But there's also more regional effects in the Mediterranean. I don't know, wind along the coast in westerly direction and the one side and easterly direction on the other side, and then maybe pushing water together in one location along the coast. And then, so there is, if you look at a regional model of the Mediterranean Sea, which is wind forcing applied, there will be some water level variations due to that atmospheric forcing. The largest part of that atmosphere, or another part of that atmospheric forcing, sorry, let me go one step back. So the storm surge now, we sort of have separated into two parts. The one is the regional search, and the other one is the shallow water search. And that's a little bit of a technical separation because we need to define somewhere where we put our boundary condition, right? So if we put our boundary condition here and I have wind forcing here, then I will resolve this part in my model. But then the other part, I rely on that is correctly resolved in my regional model. So that's why there is these two combinations. Okay, which part of the wind impact do I resolve in my model, and which other residual part do I not resolve? And then there's a barometric search, and that is due to pressure variations. So there is a low and a high pressure. Under the high pressure, we have a depression, and under the low pressure, we have an increase and a water exchange between the two. But these pressure systems move very slowly, and they also are very large. So when you model 4 kilometers away from the coast, your pressure is sort of constant in that part of the domain. So there is no water level variations due to pressure variations within your coastal model. Any water level variations because of pressure are just a part of the residual, and they are included in the extreme value analysis of water levels and thereby included in the boundary condition. So these three guys here are the irregular water level variations. And the regional search and the barometric search are just together in the boundary condition. And in fact, we cannot really separate it. What all we can do is we can take a model of the Mediterranean Sea and extract the water level some distance offshore, and we can perform a tidal analysis. So we find the harmonic variation, and then we know, okay, this part is tide, and the rest is residual. And then we don't really know, without doing further analysis of pressure systems, etc., we don't know which part of the residual is now a search and a barometric search. But it's also irrelevant because both of these components are just applied on the boundary. But what we do know is that there will be additional water levels set up due to the shallow water search, so the local wind forcing on the body of water that we model in our 4-kilometer coastal profile. So yeah, I hope that gave some more insight now formulating it yet with other words, and otherwise we can take the discussion maybe a bit further at the end of also tomorrow after we have maybe a little bit more hands-on examples. But yeah, I hope that helped, the additional explanation. Did we?
Okay, go ahead.
Yeah. Okay. Good. Then we have 4 examples. I suggest should we take 2 and then a small coffee break and then another 2, maybe something like that, or maybe one actually, then a small coffee break and then the other 3, because I think it will take a little bit longer to go through the first one than through the other ones. So the first academic example one can almost say is just a wind setup on a lake. And it's actually the first example of the DHI that's included in the mic installation that I adapted here. So it's just the domain 5 kilometer long and 10 meter deep. And the scope that I want to go through is that we make a copy, that we make a template setup of this with the wind speed, with the wind speed forcing. And we test the template that it's running and that we get results. And then from that, we want to make a batch setup. And what we want to do is we want to modify the wind speed that we're forcing here to a range of wind speeds. After we've done the batch files, I'll show you quickly how you can manually check if the batch files were run correctly. Then we can run the setups. I've already pre-run them, so we saved time, and then we can compare some results. And for the results, we also compare to the analytical solution. For the for the wind setup of a lake, it's a very simple analytical solution, which also is in the user manual. So it's a function of the shear stress by the wind onto the water surface. You all know this term well, with the drag coefficient and the density of the air. And then you do a force balance of that water level setup in the lake. So you can imagine on the it goes up, and that hydrostatic pressure difference forces a force on in the opposite direction of the wind, and that needs to be to balance the shear stress. And then you can rearrange this, and you have that water analytical expression for the water level setup. So now we go to the example, and let me first quickly reveal it in the file explorer. So I have these examples, and I'm suggesting that I also just deliver them with the course material. I don't know who of you is into Python or not, but I will also save an HTML of the so-called notebooks that we're looking at now, so you can also look at all the things without any Python knowledge. But so the first example is the that we want to take a template, and that is this one here, and let's just look at it. And I already prepared it a little bit. No, this one was actually not modified. So it points to the mesh time. We just do 4 hours of simulation. And then the main thing that we have here is that we include a constant wind forcing. In the template, 35. Yes?
Maximize your window. Maximize mic window.
What's that?
Maximize. Make the window of
maximize. Yes. Sorry. Yes. Yes. Maximize the window. I can't zoom, unfortunately. I think. Can you see it? Okay. Or yeah. Still small. What do we do? What do we do? Now, if I go to my other screen, let me try one thing. Bear with me. Let me try to change the resolution of my screen. If this is a good idea. I don't know. I'm going out of the display settings, identify to scale. 125.
There are one suggestion that you can try control plus scroll in mic.
Okay.
Try control, press control and scroll.
No, I tried. I tried. I did increase my screen, or the scaling of the screen I changed now. Is it a little bit bigger now? Okay. I think that's what I can do. I hope it should be bigger now. At least on my screen it shows much bigger. I don't know if then the presentation will show okay, but we will see. Okay. Thanks for your patience. So, and then there's basically a wind forcing 35 meters per second in the template to 70 degrees. So it blows from east to west. And then we just do a few outputs. I didn't change anything here compared to the template. So an area output, and then the output 2 is a point here in the end where we output the water level. All right, so we close this again, and now I go into and I do this real time now, so I hope everything goes well, but I've saved also a run version in case something goes wrong. So if I have now this folder here, right, with this, and I've, by the way, also tested this template, so I called it Lake 0. I tested it, it runs fine. And now I want to investigate the impact of the wind speed. And for that, I made a little Python notebook. So I import some packages. Mic.io is the Python DHI Python package I can highly recommend for interacting with mic files and PFS files. And now I define the model cases, some pandas. Don't worry about this. You can look at it if you're not familiar with it afterwards. But what I'm doing here is basically I create a table. In this guy here, I create this table. So I say case 1, and I want to make a setup called lake 1. Case 2, I want to make a setup lake 2, and so on. And I want to vary the wind speed from 0 to 40 in 5 meter per second steps. So that's my goal. I wanna set up all these. And now I make the setup files, and let's go through that step by step. So I first point to the template that we just looked at, and then I choose a model directory where I want to save the modified ones. And if I just split this here, so then now here I loop through the model cases and I modify the PFS and save it. But I go through that now a little bit step by step. So if I run this, I go now here through my 9 model cases, and now we're actually in this part of the loop where it's at 9. So we can quickly look at it. So row is one row of the data frame. So when I now look at row, like this is now case 9. Setup name this guy and wind speed 40. So here in this row, I now have the information that I want to apply for that run. And then PFS, what is that PFS thing? Well, that PFS is actually a handler where I now can interact with my PFS setup file. So here I have basically simple the whole PFS file as an input. But it is even a little bit smarter than that, because it can then, if you start to autocomplete here, then you find these guys. So if I go HD, I have the HD engine. And then I want to do something with the wind forcing. Then I can go to the section wind forcing, and then I have this section. So that's basically how it works. And to find these ones, it is always a little bit of an interactive thing of, looking in the GUI, or sometimes I just open this in a notepad, and then I just quickly go for search for wind. Okay, there's no, so it's case sensitive. Wind forcing. Okay, so there's somewhere a section wind forcing, and then there's a constant speed, and it's basically this guy here, the 35, that I want to vary, right, for the different wind speeds. And I don't want to do that in the GUI because it's too many cases. And that's the same principle later, actually, that is also used to set up all these hundreds of model runs for the ICZM project. So this first, I hope I'm not boring any one of you, but I go through that first example just step by step, and then we know how to do it, and we will use the same approach. And by the way, there's many ways of doing it. You can also, modify this text file in any other way that you want. But for me, the mic.io works well. Samir, you have a question?
Let me clarify your objectives.
Yes. Yeah. Maybe I go to this table here for your.
Yes. Great.
Yeah.
Great. The objective to run many parametric study. Do you remember? We would like to make a parametric study using different wave speeds from 0 to 40. But we are going to do it by coding, not manually. يعني الويند سبيد. احنا ممكن نعملها مانيوالي، يعني ممكن احنا كنا بنحل الموديل كنا عاملين نأديت الفلوسيتي مانيوالي، كنا مغيرينها نخليها مثلا 35 35 40 20 and run the case. Here Henrik would like to show another approach which is by coding. يعني هنتحكم في البرنامج بالكود. ها؟ برمجه باستخدام فيجوال ستوديو كود. هنتحكم ونأديت بدل ما نأديت مانوالي نخليها اوتوماتيك. اللي هو ده اسمه فيجوال ستوديو كود. ده واحد من الانفايرمنت اللي بتستخدم للبرمجه. وهنا هيبرمج فيها بايثون. يعني فيجوال ستوديو كود يقدر يبرمج لغات كتير قوي. هو اختار البايثون، والبايثون في لايبرري مرتبطه بالمايك اللي هو عرفها في البدايه خالص، في الاول خالص عمل امبورت للمايك لايبرري او الهيدر فايلز بتاعت المايك اللي بتخلي البايثون كنترول اور اديت ذا مايك فايلز. هناخد من كل الحاجات دي بس فاهمين الاوبجيكتيف؟ اوكي. Go into more details. This is the objective. Go into details. Okay, Henry?
Yeah, and I will also, I don't know if you're into Python, but I will also distribute like an environment file so you can set it up in the same way. And these are IPython notebooks, they are called. This is this extension .ipy notebook. And I chose that rather than Python scripts because you can also open that in a Jupyter notebook of however you want to open it. Visual Studio Code is my preferred, GUI. It's also freeware. I can highly recommend it, but this is maybe a little bit outside the scope. But I will save these guys also, as I said, as a HTML or PDF, so you can also look at the steps if you don't yet have Python. But I can really recommend looking into this. It's a very powerful tool. Like if you go maybe 3-4 cases, you probably, there's a little bit, let's say, a little bit of a steep learning curve, right? Like the first time you do it, you're like, I just copy paste this 4 times and change the wind speed and I'm ready. But then we also use this whole same, let's say, approach for the post processing. And then once you have more cases and more variables, it's it's impossible almost to do it manually. Or if you attempt to do it manually, there's also a large chance of errors. Here's also a chance of errors when you write a code. But the good thing is that if you make an error, you make the same error everywhere, so you're likely to pick it up. And if you fix an error, you also fix the error everywhere. So it's really I highly recommend if you need to get into many model cases to have a look at this approach. Right. So now we have the wind forcing, and basically what I'm now doing here is so the HD wind forcing. Let's just execute this again. So sorry, I have not run this yet. So it's 35. So in our template, the constant wind speed is 35. But now I replace it with the value of that case, which is 40. And now I don't do more on the fly before I completely break my code. But as I told you, I also saved a backup because these live presentations are always a bit risky. Now I run the whole loop, and now it goes through the 9 setups, and I just give a little backup feedback here, saved, batch, etc. And now if we go back to our folder, voila, now I don't have lake 0 only, I have lake 1 to 9. And as I said, the next step would be a manual test then of these batch files that I always recommend. So if we now, for example, just open lake 4, there's 2 ways of manual checking it. I show you both. One is to then open, so this we just generated programmatically. If I then, or in the code. So if I then open this all still needs to be green. If then all of a sudden something is red, then I've coded something wrong. It's still all green. Okay, let's go to the wind forcing. It's 15. So case 4, 50 meter per second. Okay, let's go back to our table. Case 4, 50 meter per second. Okay, looks like it worked okay. That's one way of checking it. Another powerful way of checking it I find is, let's for example compare these 2 guys. Edit in notebook. Our template, our case 8. Plugins, compare, boom, now you get all the differences. And now we go through them. Okay, bad example because 8 is exactly the template. Let's take another one. We take the template and 4. Plugins, compare. And now we go to the, you see there's quite a few differences, and that is a little bit annoying. Somehow after it's gone through Python, there's like more digits here, but it's the same number, right? So in the template, less digits, sorry, it rounds. In the template, it's, for example, this guy here is 0.692999, here's 3. So you get all this. Here on the right, you see all the differences. You get all these differences, and most of them are not differences in practice. But what we changed is the wind speed. So in the 0, it's 35, and then in case 4, it's 15. Okay, so we are happy with it. Now I want to run all these. And then to run all these, I make another little thing, and that's I make a batch file. So now here I programmatically write a little text file. Here I first print it. So this is the text. I set my path to the mic 24, and then I say start simulation leg 1, wait until it finishes, start simulation 2, etc. And now I save the batch file. Back to here, now I have a batch file. If I open this and edit, voila, now I have my batch file here to run the 9 model runs. Yes?
Can you send us these files such that they watch the file at the same time as you, or?
I'm running the models, you mean?
No, I'm talking about this file. This
the notebook.
The code.
Yeah. Are you all in?
Notepad. We can open it using Notepad or something like this.
Oh, you can also use Notepad. I'm just a little bit afraid, Samir. I think it's a good idea, but that's what I said initially. I'm a little bit afraid that if it works in the format now, that, you know, if I was in the same room, I would do it exactly like that, to say, okay, we do it and the pause, and then there's problems and I can go around. I'm just a little bit afraid that if we try this now, that we get stuck in technical issues. But I will immediately share all these examples afterwards, and then you can maybe try, and then we can pick it up. And you can, if you get stuck, you can send me an email, or in light of time, I have a little bit of doubt if that's a success. But
I see.
Yeah.
Okay. The objective now is to run. We are already creating the mistake.
الفكره ان احنا مش شايفين الحاجه اللي بتتغير فيها. مش شايفين هو اللاين هو بيشرح حاجه. يعني هو طبيعي بيغير في هو كده هيركب الفايل ده. ايوه. السكريبت ده. السكريبت. مش عارفين اصلا عشان
Can you enlarge the font size inside the notepad? Just edit font size or something like this.
In the notepad. Is this? Can you see the notebook? Okay. Can you see this? Okay, or is it also too small? Yeah, I can enlarge.
دلوقتي هيزود السايز هنشيل فوق every line.
But let me here I cannot enlarge, but let me, you know what, I just tried to push this to the limit here. I haven't tried that before, but like, let's say, okay. Okay, so that's a maximum. Did it get a bit larger, or?
يعني هي الفكره انك انت ممكن تشتغل مانيوال وممكن تشتغل برمجه. فلما بتبقى الكيسز كتير قوي والرانز كتير قوي انت تشتغل برمجه، فدي ادفانسد ستيب. هو بيوريك ازاي احسن لما يكون الشغل كتير. يعني لو هتعمل 3 كيسز خلاص، يعني مانيوال كتير. انما لو هتعمل 20 كيس
ده زي ماكرو كده.
ده ماكرو سكريبت بس بايثون سكريبت، وده الكود، ده الجزء بتاع الكود، وده الجزء بتاع الاوت بتاع الكود. ده بيرن حاجه اسمها باتش فايل. طبعا عشان الباك جراوند بتاعكم مش عالي قوي في البروجرامينج، لكن هو الراجل بيتكلم على حاجات انتجريتد كودينج، يعني البايثون مع الباتش مع الويندوز مع
Samir, I have one idea. We could tomorrow. I have 2 sessions.
Yes.
I could take the 2 topics a bit shorter and put them together in the first session. So the first session I present the 2 topics, and then the second session we could do like a question and answers, whatever. And so I could, after my presentation today, immediately share all these files with you. And you can, the later today or in the evening, the interested students can have a look at it and try to run it, and then you can come back with questions for the second part of tomorrow, where we try to resolve these questions.
Okay, great.
Yeah?
Great. Yes. Please go ahead. Yes.
Let's do it like that. Yeah. Yes. Next time you just need to find some money for a flight ticket, Samir, and then we can we can do it in Egypt in person. Okay. So yeah, I also, my apologies for going through it maybe a bit fast, but so the idea again, okay, what's a batch file? The idea with that is that I can now double click on this and the execution will be launched according to this. So instead of basically right click, open each model file separately, I can execute it here. Now that we won't do now, because I already saved a copy to save us the time, which was the same folder, but there I had already executed the batch file. So now the models are already all run. So you get the familiar log file next to the model run, and you also get the familiar result files, standard output folder per model run. So this was our template, and now for the 9 cases that we have defined, we have result files. And then before I continue with the coding, I always like to, and I just show you that now as well, I always like to still do it a little bit sort of semi, let's say like some spot checks, before I check the 3 and the 1, and now I just more or less randomly open the log file of the case 6, and I go to the bottom and normal run completion, okay. I just go to the results of another one. I have my 2 result files, time series, just open it manually. Okay, it looks like that. I think it's a good idea to just still do these manual checks sometimes, because when you code, you can sometimes you just accidentally point to a different file and you make all your fancy stuff and you don't realize that actually you're looking at completely the wrong data. So kind of staying manually in touch with your model results outside your code environment is just a recommendation from my side. So now we want to analyze the model results. And there I do a few steps. So first is to load the model results. And that's, or load selected model results. And as I wrote here, there's many ways to achieve this, and also depending on the file size. So if you, of course, have large model domains and large models, and in many cases, you cannot just load all the results to memory and then do your processing analysis. You need to be smarter about it. But here, to keep the example a little bit simple, and it's a small test case, I mean, we can like quickly look at these cases here. If I mark them all and I go to properties, I mean, we have a total of 5 megabytes of all our model results, right? So memory is not an issue here. So we can keep it a bit simple. And what I now do is I simply load all these model results to a so-called dictionary. But let's go through that here step by step again. So df, this was our table here at the top, right? If I quickly put df here. So this is our table with the cases and the wind speed. And now I loop again through the rows of this table, 1 to 9, and then I have the row, which is one row of that, now the case 9 with that setup. And now I want to load the results of that case. So the first thing is I need to construct the file name. So I say, okay, the result dir is the setup name minus result files. And then I join that with the model dir. So now this is my file name. Now I constructed the file name. Okay, my file name is batch, and now I actually saw that I forgot to run this. So now I set the model dir to where I already have the results. And now I construct this file name. So I'm pointing to batch run lake 9 21 FM result files TS DFS0. So I'm now in that case pointing to this file, right? In my code. So for each case. And now I load this as a MikeIO dataset. So it's simply load and done. And let's just quickly look at what that is. Now I have a MikeIO dataset. Okay. Now let me put this back together. Now we now I went through this loop step by step, but now I do this loop for all my 9 result cases. So I find the file and then I load it, and then finally I save my results to a dictionary, it's called. And now explore. So now I have this result. Okay, what is that result? Let's have a look at it. Okay, it's a dictionary. Result 1, MikeIO dataset. Result 2, MikeIO dataset, and so on forth. So if we take the fourth item of results, then that will be the dataset of case 4. Here it is, MikeIO dataset of case 4. If of that case 4, I take the number 0 item, 0.1, and plot it, I get this. Okay, here it is. My result, right? The one I think we looked actually at case 4 just before, right? It went up to 3.5 centimeters. So instead of opening it manually, I now have it here programmatically. Again, I'm going quite fast through it now, and I appreciate that you will have to go through that example again yourself and try and error. But once you get the spirit of it, it is really a great tool, and that's why I decided also to present it here today. And then you can see the water level sort of goes up because we defined actually a ramp up for the wind speed, and then it sort of finds equilibrium here, and it's not 100% stable, the numerical solution. So now we want to find the equilibrium water levels, and for that I just say, okay, if we look at the time, this is the timestamps of our results. It goes from 00 to 4, so it's 4 hours. And now I say, okay, the start time from where I want to consider my result is at 3 hours. So this one. And then I say, okay, over the last hour, I take the average value and take that as the final water level. That final water level I add to the data frame of my cases. So let's run that. Okay, now I have my cases 1 to 9. My setup name, the wind speed that I applied, and the final water level. And now here I don't go through that step by step, but that's just basically making a plot of the results. Let's plot that and have a look at it. So now I have water level at 0.1 for my 9 water cases of wind speed. Case 1, 0 meter per second, the blue line down here. And up to 9, the 40. And then the dashed one is the average water level that I computed for the last hour. So for example, here, for that case, it's quite, you can see that is the average of that curve. So now I compared these across all the 9 cases, the evolution of the water level at 0.1. Now we go to the analytical solution. Let's check the, let's go back actually 1 second to the analytical solution. So it's a drag coefficient, density of the air, density of the water, and that, of course, we want to have as in the model. So we quickly look at the wind forcing, and then we can see that the drag coefficient is constant friction. It's here. So we now define the analytical solution where for the density of air, we take this guy. For the drag coefficient, we take it right from the PFS file of the model. So we take the same as in the model. Then we compute friction, which is the density of the air times drag coefficient times the wind speed of that case raised to the power of 2. That's like a little Python guy here. If you know MATLAB, I think it would be something like that. No, but in Python, it's 2 stars is a to the power 2. And then we compute the water level setup. So gravity, density of the water, the length. In our case, the sea was 4,900 meter long, and it was 10 meter deep. So we also add that. So now we have our big table here again, the case, the setup, the wind speed that we applied, the final water level, the theoretical surface tension, and the water level analytical. And you can already see here, it's quite nice match. But now we can also compare the final water levels versus wind speed, just plotting from this table. And we do that here. So now we have the wind speed. Here's our cases that we run, 0, 5, 10, 15, 20, 25, 30, 35, 40. The blue one, the mic result, and the orange one, the analytical solution. And with that, I'm at the end of the example 1. I hope you got you got some at least let's say inspiration on how you can also approach setting up these model batch runs, and also get an idea or get now the confirmation that at least for the simple example of a lake, the Mike model does a pretty good job to be in line with the analytical solution. So although we discussed that I share this, and then there's room for questions on this tomorrow, are there any immediate questions now on this setup? On this example? Any questions? Yeah.
هل في أسئلة دلوقتي؟ Okay, thank you. We can take.
What's that? No.
Are we going to take a break now?
Should we take a little break, or yeah? I have 3 more examples. I think through the other 3 examples, I just more show the results. But I think it fits well with a break now. I think it's halfway of my presentation. Yeah.
Okay. Thank you. We can take a break up to.
Okay, you let me know. I'm ready.
Yes, we are ready, Eric. We can start now.
Okay. So, quick recap. We did the first example of the lake, where we varied the wind speed over from 0 to 40 in 5 meters per second steps, and we compared we set up the batch files, and we run the models, and we loaded the results, and we compared this here, the model result versus the analytical solution. The next example is now that we want to look at the wind setup on along the coast, which of course is much more relevant to the project we are looking at. And the scopes of that example is to make a mesh with a simple coastal profile which I prepared, but I will give you the files. You can look at it. Again, make a template and test the template, batch setups, run the setups, which I pre-run and compare the results. So I prepared a domain like this. I left the same length of 4,900 meters and a somewhat arbitrary set at 5 kilometers offshore. It's 100 meter deep. It goes to around 10 meter, some 800 meter offshore or so, and then it goes up to 2 meters onshore. Yeah, it's arbitrary, simple, but also not completely off profiles you can find along the coast in Egypt. So the first step, as I said, is to make a little mesh. So let's do that. So yeah, I did, as I said, that's a coastal profile that I defined. And that I, to be honest, did not do in a code. You could also code that. But I basically, in Excel, manually defined a little XYZ to do that, to represent that profile. And then in the MDF, I included that XYZ. You will have these files as well. Maybe there's smarter ways of doing it, but then here I basically did the interpolation and I end up with that. You could now also argue in such a 2D case, why don't you use box contours? But I stuck to the unstructured mesh because it's in real life we have an unstructured mesh, so it's also nice to get a feeling a little bit for numerical dispersion and these sort of effects. And of course, it's quite a coarse mesh for these simple examples. But yeah, we go from -100 to around 10 somewhere here, and then to around 2 meters at the end of the domain. And then in terms of how do I get? Does anyone know how I get rid of this thing here at the top of content only standard? Oh, nej, det vil jeg ikke. Does anyone know how I get rid of the this navigate? Maybe you guys don't see it, but I have this sort of Teams navigation bar at the top of my screen, which means that I cannot properly navigate, and it was not there just before. My apologies, but I stopped sharing and quickly try to start sharing again. It pops up again. Anyhow, I try to survive with it because now I cannot reach the code value button. Okay, now it disappeared. And that's the boundary code values I defined. So here on the eastern boundary or the offshore boundary 2, so we can define that in the model, and then the rest is a 1, which is the default code value for a land boundary. And I don't need to save that. So that's a mesh. And then the first step is again to set up a template, which is this one here. So let's have a look at that. So I have my domain here. And then I like to give the boundaries names. So code 2, there was only 2, is the offshore boundary. And then I just saw then we have the wind forcing again, constant value that's included. That's again the guy that we wanna vary, right? And then actually maybe we could have thought about for the first example, okay, which steps would have been actually included to do that comparison with the analytical solution manually? Well, then you would have had to copy this setup file 9 times and then open each setup file and change the value here, right? And then you would have to open the result files and get out the result, etc., etc. So there's a lot of steps that we now put into a script to do it systematically. So that's a constant wind and then outputs. I added one output compared to the one before, that we also take a profile along the domain. And then boundary conditions. I just want to reuse this example. I could have also defined it with another boundary, but for now the offshore boundary is just a 0 water level, because and then the rest are land boundaries. So here are our boundaries offshore and then land boundaries. And I put it just to 0 meters. Because for now, in this example, we want to look at the impact of the wind speed, but in the other examples, we will make use of that boundary condition. So that is the template, and I've already run it. I checked that the log file is successful, and here are the results. And let's just quickly look at the profile. At the last profile, then I get this water level set up due to the shallow water wind of 10 centimeters near the coast, in that case of the template. Okay, now we have a template, and now we want to again define some scenarios and set up the model runs, etc., etc. And now I have again prepared a script for that, and we will probably go to it not so much step by step this time, but let's see. So it's in the 1.2 example, the wind setup on the coast. I deleted everything, all the outputs. So I import the packages that I'm using. Then I'm building my table again. It's very similar to the first one, only that I now named the setup coast 1, 2, 3, 4, 5. And now I also, just to save some time on computation, when I run the examples, I increase the wind speed from 0 to 40 in 10 meters per second steps. So this is our little case table that we're going to use again. Then I'm going to make the setup files. So this time I now go to that template that we just looked at. And this is, of course, all for you to modify if you use such a framework in your projects. You will have your own folder structure. You will have your own file name convention. For example, in the ICZM models, in the ICZM project, these are actually defined as the file name convention was chosen based on the load cases. Here, I just simply went from case 1 to 5. There you need to find a good balance. But one recommendation here on the side is don't try to save all information in the file name, because you end up with very long file names, and that at the end you have not all the information that you need anyway. So come up with some sort of a good file name convention, and then keep track of the setups in such a table, and you could also save such a table to Excel. So that's just a little recommendation from my side. I sometimes see this, that people try to save everything in the file name, wind speed, HS, boundary condition, and then probably in the end final version 2, etc. So keep the file names a little bit simple if possible. Like the load cases, I think is a very, very good convention that was chosen for the ICZM project. And now we loop again over the cases, and we do exactly the same as before. We load the PFS file, we modify the wind forcing, and we save it. So we can just run that. And then just for good practice, I also do it here again. So now here these popped up. Yeah, they just popped up now, 1023. So just for good practice, let's open these two in Notepad, and then plugins, compare. Again, I get all these differences here because of the rounding. And then there's also some formatting issue now, but that's not so relevant. But here I changed now the constant speed from 35 in the template to 10 in the case 2, and that from memory is correct. But then let's also open one and everything is fine here, right? Everything is still on green. So we can have a quick look at the wind forcing. Sorry, not the friction, the forcing. Now the speed is 10 meters per second in that case. And then as before, I make a batch file to run these examples, and then I save the batch file. So now also this batch file popped up here, where I call the MZ launch engine on these 5 model runs. I wait until the model run is completed, and then I go to the next one. And now you could just double click, and in fact, actually it wouldn't take too long to just double click and run it here, but it still takes some, I don't know, 5-10 minutes, and while I'm online, etc. So I didn't want to take the risk, but I already have a copy here where the model runs are executed. So now we have our 5 result folders. And as I said before, it's also a good practice to quickly familiarize yourself a little bit with these results outside the coding. So I look, for example, at the last one, and that the last case 5 goes up to just above 10 centimeters. So I would then now keep that in mind, that result, and see if I find that again when I now process the results in the code. So again, I now set the model directory to the folder where I've already run the results, where I already have them. If you execute the guy here and the results are here, you could also stay in this folder here. But again, this bookkeeping, etc., that's always a little bit, it's no black and white. You know, this is one suggestion how it works. You can come up with your own, or as a team, you might come up with conventions. So that's just a recommendation here, or one example of doing it. So now my model dir is this one. I overrode it, and now I'll load the results. This time, now it starts a bit different. Now it is different from the previous example. I save 2 types of results. One is again the time series in point 1, and the other one is a profile. And here I take the last time step. So here I initiate dictionaries, like containers where I save my results. And then I loop over my cases. And then here I load the point 1. So I construct the, and maybe let's take this a little bit in sections. So I loop over my 5 cases. Now the loop is in case 5. So right now I'm in the last case. So now I construct this, and then I have batch run, coast 5, model results files, time series DFS0. That's the name that I've constructed here. And now I can load this as a DS, and here I save it to the results. Alt Windows J, that's always something I forget. Alt Windows J, join with next one. So, and then I save the results to my dictionary. So then I have my time series from point 1 saved, and then I do the same with the profile. I construct the file name, but now I'm pointing to another file name, right? Because I saved the profile in as a DFS1. So my file name is now coast 5 result files profile DFS1. And now I load it as a DS, but actually I do another little trick here already inside the loading. That's something that you will find yourself doing when your result files become bigger and bigger and bigger, that you only load what you actually need. And what I load here is the last time step. You can look at the Mike.io documentation to figure out all the options that you have. So now this data set here is called time invariant because it's only one timestamp. It's only the last timestamp, and then I have the item surface elevation U and V. And then again, I also save it to the result dictionary, which I called results 2. Again, it's not very not very creative naming conventions, but my experience again is try to keep the names as descriptive and as short as possible for your variables in your code environment, because if they become too non-descriptive, it's hard to follow, but if they become too long, it's also hard to follow. So there you will find your own way. And now I put it all back together, and now I looped over it and have the results here saved. So now let's exploit the result dictionary and the fourth item of it. That will be the data set of case 4 and the data set of case 4. And then out of that, item 0 is the surface elevation so that we can plot. And that goes up to 006. I think we did not look at case 4 before. We looked at case 5. So let's quickly look at case 4. That's again a quick manual double check if I'm doing my bookkeeping correct. Yeah, it goes here up to 058, right? This is this. So again, these sort of quick checks here and there. Am I looking at the right data? Am I doing my bookkeeping right? Is highly recommended. Then the results 2. I could look at case 4. That's my time invariant data set, and then I select the item 0 and I plot it, and I get this sort of profile. And that is, we don't need to double check that again because I can see that this is correct here where the point is extracted. So that's, now we have our results. Now again, I get the equilibrium water level. I take the last hour, T0 I define as 3, and the simulation goes until 4. And then I take the mean over here. I select the last hour of my time series and I take the mean, and then I add the final water level to my data frame. And then I get this data frame again. Setup, wind speed, final water level. And then I do a plot. One is, for example, compare the time series. So here I have the 5 cases for the different wind speeds that we run, and that's how the water level at point 1 goes up. This I actually didn't, my apologies, I actually didn't get to implementing the analytical solution for this case, so that I need to delete. That you can have a look at yourself if you're keen. The analytical solution was in the presentation for the shallow water setup. Maybe we can take that tomorrow in the Q&A. And then I compare the final water level for the different wind speeds. So from 0 to 40 from the 5 model runs that we run. And then I can also compare the water level profiles. So profiles is along the domain. So from 0 to 4,900 meter, blue is down here. There's a slightly that's got something to do with the flooding of these are the elements that are above 0. So and then the interpolation from the unstructured mesh, etc. So that of course, yeah. So that's sort of the initial. Yeah, that's a reason for that. But otherwise, here you can nicely see the water, and that's now what we called in our presentation before. That's sort of the shallow water level setup. So let's say we have shallow our domain was from 100 meters, but let's say we have a 40 meter per second. Let's actually look at our profile again. So we're looking at this profile from 100 meter to 10. So over that profile, and we apply 20 meter per second, maybe, then we have a contribution at the coast of 2 centimeters of shallow water setup. And if my boundary, or let's take the purple line, the 40 meters per second, then I actually go to 10 centimeters. and that is, you can see here in the deep water, here's 100 meters, maybe here's 90, etc. So in the deep water, there's not much happening with that setup. So you can say if your boundary is all the way out here, it is probably okay to assume that there is no shallow water setup outside your boundary condition. But if you wanted to really have a very small coastal domain, for example, you go, for whatever reason, you only model it from 10 meters, so you go 500 meters to the coast, then you would already, what I'm pointing at now, if you set up such a model, you could already have a shallow water level setup of 5 centimeter at your boundary condition. So then you would have to compute it yourself beforehand and include it in the boundary condition. So that's what we discussed before, that it depends on where your boundary condition of the offshore boundary is located, how this is distributed. So yeah, that was the second example, wind speed over a constant wind speed over a coastal profile. Save this, and then I clean it up and I'll distribute it as soon as possible. We move to the third example. Yes?
Before going to the third example,
yes.
would like to ask for any questions.
Yes, sorry, my apologies.
هيبقى كل زي مكتوب زي ده كده بالظبط، كل خطوه هيبقى شرح فيها من فوق هو بيعمل ايه وهو بالظبط.
Okay. The first question was related to the script you are going to send us will be containing all the comments, isn't it?
Yeah, I will just send you this whole folder. No.
Okay.
No secrets.
Sure. Second. Mesh resolution, is there any restrictions about the mesh resolutions you are using?
Yeah, well, of course, if it was a whole modeling exercise, as I think we discussed in the first one, you would have to now look at things like model convergence, like increasing the resolution, etc. But I didn't look at that here. So it's a very coarse, very rough example mesh, if that was the question regarding limit. And also it is a simple profile, right? So of course, it's kind of an idealized 1D problem actually, because there's no water level variation other than introduced by the coarse unstructured mesh in the cross-shore direction. Of course, in the real world, you would be setting up a local model for some real bathymetry, and you would have to start to look at preparing your bathymetry, mesh conversions, etc., etc. That I excluded now from this example. Here I wanted to focus on this simple example, where actually an analytical solution exists. But my apologies, I haven't put it in. It was this one here. So it's you can iteratively solve this in a forward scheme. So if you say there's 0 water level set up here, then you can work your way along a profile and work out that water level setup. So for this 1D scenario, and then of course the moment you are in the real world and doing your real examples, then no analytical solutions exist anymore. But it gives a good idea still, because we used an arbitrary profile, but it is somewhat representative of real profiles you can find along the north coast in Egypt. Like if you zoom out all the way, if you like really on a big scale, where's the 100-meter contour, where's the 10-meter contour, you could find something like that. And that means that these order of magnitudes here are probably not far off. So you immediately see that, of course, the offshore boundary, the search that you have there, even the tidal contribution, the climate change is actually the biggest one in our project here, are more important than this shallow water level setup. But again, it gives up to 10 centimeters, and if you add all these small contributions, I mean, that's why we set up models. We want to be as accurate as possible. But it's not a major contribution in the ICZM project, to put it like that. Yeah.
هل نقدر نحسب الموضوع نقول ان هو ده تاثير الويند سيت اب مثلا حتى لو كان كده يبقى ليش ولا لا؟ السؤال الاول. السؤال الثاني بقى هل البروفايل سلوب هيبقى سنسيتيف ولا لا؟ يعني البروفايل سلوب ليه القاع نفسه معايا هيبقى سنسيتيف ولا لا في الويند سيت اب؟ بالتالي الضوء مني انا مش هحضر الثلاثه دول قولني واحد واحد. ماشي واحد اول حاجه اولانيه هل انا كده اقدر اقول ان الويند سيت اب تاثيره محدود جدا مع 10 سم؟
The first question is related to the wind setup value. Is it
Yes.
In this example? It shows that it is around 10 centimeters for wind speed 40 meters per second.
Yes.
So is it? We can say that usually the wind setup is within 10 centimeters and small, not so big or not affected our domains.
Yeah, that's what I said before. In our case here, it is indeed not a major contribution to flood events, but it is also. I would still include it. I mean, it's of the same order as magnitude as the tidal contribution, right? Which is also plus minus 10 centimeters. But yes, you're correct. It's a small in this at this site. It's a small contribution. Water level climate change scenario plus land subsidence, wasn't it of the order? Correct me if I'm wrong, but I want to say something like 60 centimeters or something like that. So yeah. And then the water level extremes on the offshore boundary, so including the regional surge and the barometric did I include it in the presentation? No. Yes. Here, these are the storm profiles, right? That were extracted on the boundary. So there, the peak goes up to, and that's without climate change contribution. But there, the peaks go up to half a meter at the offshore boundary. So, I mean, it does 40 meters per second is also quite strong. But let's say the 20, it contributes 2 centimeters. Yeah, you would hardly see it on this one. But if you then 2 centimeters that, and then the tide, and then the wave setup, you add probably like a 10% or something like that to this. Yeah, it's not very expensive to compute it, so you might as well include the wind forcing. But yeah.
The second point is related to the bend slope. Is it sensitive in the calculation of the wave setup and the domain size?
Sorry, the first part was the wind. What's the
bed slope?
Yes. Good one. No, yes, it is in the sense that it's accumulative. So if we look at the analytical solution, is the more you get more wind setup in shallow water. So if you have in your profile a steep slope in the beginning and then a lot of shallow water, then you get more wind setup because you get more wind setup here versus deep water and then a steep slope. But it's not but the slope itself doesn't go in as a parameter. It's the instantaneous water depth along your profile that are going into this equation. So the shape, the bottom contour of your profile has an impact, yes. And the more shallow the water, the greater the effect. So if you have a reef, if your 10-meter contour is 2,000 meters out, or you have some estuaries or whatever, if you have large areas with shallow water, then you're closer to that example 1, right? In example 1, we just had a lake of 10 meters water depth. So if you have areas like that, then you get larger setups. And then the second part, what was the second component? That was the slope. And the second part of that question?
Domain size.
Domain size, yes. So that's again also the how long that fetches. But here we can sort of see the domain. Like our domain here is, let's say, long enough, right? Because here on the first 1,000 meters where it goes from 100 to maybe 90 meters here, not much is happening. So if we went out another 1 kilometer and the depth was even greater, it would not have a large impact on our results. But it's like a dummy bathymetry, so you would have to consider it. If you, on the other hand, if our domain started here, then our domain would not be big enough for this example, right? Because then this line here would start as 0 here, and we would not take all this setup with us. But yeah, sort of rule of thumb, I would want to say if you go out to 100 meters, it's definitely safe. But yeah, that then starts to go into the specific model setup where you need to look at these aspects that cannot be covered with such a simple example. But yeah, I hope it answered your question.
Yes.
Yeah.
Yes.
الجراف اللي هو مدخل الفيلم
ايوه
في 8 ايجنتس
لا
ايوه بيجي دلوقتي مش هيسافر دلوقتي
يعني قصدي
ممكن تقسمهم عمليا
لو جرافيك
لا انا بتكلم عن مش اللي هو الفايبر كوميونيتي له تاثير
على الثقه. يعني كل ما الدومين سايز، لو الدومين سايز بقى صغير، لو ابتديت من هنا هتشوف سيت اب اقل، لكن كل ما عند سيت الرينج خلاص مش هيأثر، يعني بيحصل الفيتش كامل.
لازم
for the mesh resolution
actually كده هو يعني انا درست هو مش قد ايه بناء على ايه بس
in this example we didn't study the mesh resolution effect on our case because this is just to show the wind setup. No.
You can, I mean, there's a lot of, you can start to study the drag coefficient. You can start like it's a selected, an arbitrary, subset of the modeling exercises you probably will have to do when setting up a real. The last comment again is on this in general, when setting up a model, you can always say your boundary condition where you define a value, and our boundary condition is here that at the offshore boundary we say the water level is 0. We prescribe that. Your boundary needs to be sufficiently long away from your area of interest to not introduce an error. And that's also true here. So if you say it's 0 here, then your boundary needs to be positioned in a location where this is an okay approximation. If you wanted to place your boundary condition here, then you should compute this theoretical value, for example, and define your boundary condition as that. But then you would have to define a different boundary condition for all the different cases, etc., etc. But yeah, so that is always the case, right? Where is your boundary? What is your? How do you define the boundary? Does it affect the solution at your point of interest?
Okay, please let me clarify this point more. اختيار الباوندري كونديشن، لو الباوندري كونديشن far from the shoreline, then you can set it as 0 and no problem with that. يعني لو الباوندري كونديشن بعيد قوي، اروح الباوندري كونديشن 10 kilometers from the shoreline. there's no problem to set the wave set up the water level at this point due to the wind setup is zero. وانت بتحل المسافه بتاعتك حط زيرو مش 10 كيلومتر ما تحطش الويب سيت اب الويب سيت اب. انما لو انت واخد دومين 3 kilometers only, then you have to consider the wind setup from the analytical solution. يعني تعمل analytical expression اللي هو الاناليتيكال solution هيجيب لك مثلا هنا 2 centimeters or 3 centimeters. You have to consider this in for small domains, for small boundary condition. Okay. I have one question here, which
Yes.
is related to the 0 meter per second. Please clarify more why the blue curve. There are some setup in the blue curve around.
Yeah, I
2
don't.
meters.
I don't know exactly. I think it's some, to be quite honest. But let's look at it. Let's look at it together. The area file. We have flooding and drying activated, right? So our domain goes up to 2 meters, and then we have a. This is the initial. This is the initial water levels, and also again with quite a rough mesh, right? And then everything is zero. Okay, fine. But then you have these, and we looked at that in the first session. You have the minimum and maximum cutoff at the of the flooding and drying. So as now the wind starts blowing and the water level increases. Let's go to the. Oh, sorry, I should have not opened the. I should have not opened the case 1, but the case 5, of course. No, actually, we were interested in the case 5. In the case 1. Yeah, I simply don't know, because here in the area file, if I look at the surface elevation of the last, everything is 0. But when I have the profile extraction, I get for these. You know what? Maybe I simply extracted the wrong value. Maybe I should have not extracted the surface elevation. Yeah, no, it is also the surface elevation. But yeah, there's basically the elevation of the dry cells makes it into the result file. I don't know.
Yes, it seems for me that all results are affected by the same behavior.
Yeah.
If you return back to the plot comparing all results, I'm talking about this figure.
That I'm not so sure. I'm not so sure. Yeah.
It seems the behavior from the green and from the blue and from the red, all the last region are maybe similar. So it maybe it is due to some.
But you need to, of course, be. Yeah, you're right, and you need to, of course, be careful. The mesh that we are now looking at now is too coarse to represent the shore correctly, right? I mean, we see that here. It is like a zigzag. It's a very coarse element. So, and actually, I did also move the analysis point a little bit further offshore. So the time series here that we're looking at is a little bit is placed more here. So you would not be. Yeah, you're right. So this is something then you would have to look at in your mesh conversions, what flood levels you get on the beach, etc., etc. Yes.
Yeah.
Yes, that's correct. It is. Please keep in mind these are very basic examples, more to also demonstrate a bit the workflow of making batch files and these sort of things. But yeah, no, you need to. This is an interesting one. This could be something. If someone this could be very interesting to investigate. Also, then in a mesh convergence, if once the model, the mesh resolution is increased, would this one here disappear, or what's going on there? I simply don't know. Okay. But it's again, you then also sometimes, you know, you get then these strange things when you look at let's say theoretical examples. In a real world case where you look at real water levels and the real bathymetry and real mesh resolutions, you would never see this 2 centimeters. But of course, you want to understand where it comes from to not be concerned. I can see that. Okay. Let's leave that example here, and we go to the next example, wind speed event profile. And now that relates a little bit more to the ICZM project, where these storm profiles were established for the water level, but actually also for the wind speed, as it is written in the report. And right now we're looking at the wind speed, so we start with the wind speed. But it's a kind of this idea that you have a characteristic profile of the water level associated with a peak of the surge. You have a wave height, which is found from J-EVA, and from the wave height, you have a maximum wind speed based on an empirical solution, and then the peak significant wave heights for the different scenarios. And then you also define a wind speed profile. So the example of the CU143 return period 100 is the HMO peak is 3.8 meters, is this 100 return value. And then the wind speed from this empirical relation is 16.8 meters per second. And then the storm profile is defined from 2 meters per second up to the peak, 3 hours, and then down again. And that is what was established here to be representative. Time to peak 50 hours, peak duration 3 hours, time from peak 90 hours. And then you define this wind speed that is applied. And then now we want to also reproduce, but again with a little simplified model again. We use the same domain as before. A simple profile, and then also we only run it for 2 days, and we just go from up to a peak and hold it and go down again. So again, I want to make a template, set up the batch files, etc. So this time doing this will also involve defining DFS0 files of these storm profiles that can then be used as the input. And again, I did it all in just one notebook to set it up and to make the setup files and to look at the results. I clear all outputs. I hope I don't regret that. And then we look at this folder. So that's the example 1.3, and there's the there's our template. So I had prepared a template DFS0. That's actually, I did that in the script and then I saved it afterwards, but that's for us to look at. So this is a time series of wind speed and wind direction. Wind direction is constant from west to east, and then the wind speed goes up here and down. And then once I have this template file, I can set up my template setup, and that's the same domain as before. But then the wind forcing is now changed to varying in time, constant in domain, and I'm pointing to the template wind speed 0 DFS0 file, selecting wind speed and wind direction. And then I have this template and I run the results and everything is fine. I check that. And now I'm ready to again define cases and modify these files. So I import again my tools. I make my little table. where I have my cases 1 to 5. The names I want to give them is wind speed profile 1, 2, 3, 4, 5. And then I called it the wind speed at the peak, 0, 10, 20, 30, 40. So it's not as before anymore like a constant wind speed that is constant throughout the entire simulation. It is now the one at the peak. And then if you wanted to go into more detail, of course, you could also look at the storm duration and the window before and the window after and all these different parameters that were looked at for the ICZM project. But again, this is only one simplified example to give an idea how something like that can be done. And now I want to make the wind speed profiles. So first I define a time step. And this is an arbitrary time. I just said I start on the January the 1st and stop on the 3rd. And then I have my 2 days. Mike doesn't have relative time steps in the models. Like you cannot say, it doesn't matter if this is in 2000 or in 2100 or whatever, but you need to come up with an absolute time step for your model run. And that just needs to, of course, as you know, be in line with what you define here in your template. So I like to use something that I can remember. I usually start on January 1st, and then when you define your file here and you choose a file, you will actually get it. And now it's playing up a little bit, unfortunately, with a high resolution. But it will check if the time is covered. Otherwise, you get an error. So that I chose this here is arbitrary. You can choose whatever you want, but you just need to have it aligned with your model setup. So I define that timestamp, 4 timestamps, and then let's go through that step by step again. Then I loop the cases, and then I first define a boundary condition where I say it's a pandas data frame, and my wind speed goes from 0 to the peak, then again to the peak, and then down to 0. And my index is the time, and the wind direction is constant to 270. So what is that? Boundary condition data frame. Let's look at that. Okay, this goes from there. So it's 4 points. It's 4 data points, right? One at 0, 0 wind speed. One after a day, 40 meters. 3 hours later, 40, and then end of the simulation, 0. Now I could actually, in theory, save it like that because Mike can take care of the linear interpolation. But maybe you have some other properties of your storm profile which are not linear interpolation. So I decided to do the interpolation to 1 hour time steps already here, because then you have a more generic solution that you can also use. Maybe you wanted to use a sine function for your storm profile or whatever, So you can come up with whatever model here to define a time series. And now, after I have done the interpolation, I have a 1 hour time series. And then the next thing is that I save that on a dictionary for now, just internally. So I'm not saving it to a DFS0 just yet. That comes in the next step. So now I loop over the 5 cases. Now I have the boundary conditions dictionary with these profiles for the 5 cases. And now let's plot them. So now I'm just looping over these boundary conditions that I just defined, and I plot them. And here they are. So case 1, 0 meter per second peak. Case 2, 10 meter second peak, and so on. Right? These are the events that I would like to have. I stay 0. Here I go up to 10, stay here for 3 hours, go down to 0, etc., etc. So far, so good. Now we just need to get this guy to DFS0 so we can use it in the model. Again, I loop through my cases, and now I define a Mike.io data set. And that's how you do it. I make a data set, and then the items of that are Mike.io data arrays, and there you define the data which is for the one it's the wind speed, for the other one it's a wind direction. You define the time, and then you define the item. And this is a key component I will show you in a second again. But when I run this little piece of code, I get a Mike.io dataset. Voila. Mike.io dataset going from 49 timestamps having these two items. And now I can also ds is 0, plot the first item. Here's my wind speed. Plot the second item. And strange, by the way, when I say first, I put 0. When I say second, I put 1. That's one of these things you need to get used to with Python. It's a 0-based indexing, right? So it always starts with 0, the counting. Then I have a data set. So how do I figure out this item info? That is the properties I need to set. There is like this little EUM type. Sorry, that's a markdown. I want to have a code. By the way, when you start playing with it yourself and you want to add a little window, you have two options. One is to add a code cell. So here you can write code. And the other one is to add a markdown. So here you can write notes. And when you execute this becomes just a text. So it doesn't become any code. So that's what I just hit. And then we have this EUM type. And then the nice thing is that you can actually sort of get a drop down here of all these EUM types that are available. And there I just found wind speed, and then the units are default. And then wind direction is that one. So that I interactively found, and then I used it here. So I say the item info. The item info takes a name. This is just a name that I give it, and then a type, and then it assigns the unit. But that's enough talking. Let's just run this and see what happens. Actually, just data. It's already here. Reveal in File Explorer. I delete it again because I only wanted to have the first one. I take the risk now. And now I loop these cases. Voila, here they are. 5 DFS0 files, right? Let's look at one of them. Case 3 goes up to 20 meters per second is correct. And now the properties. And that's important, right? So here is where I defined the EUM type wind speed and the EUM type wind direction. If I did not define that, then that would not be defined here in the DFS0, and then the Mike model would not accept it as an input file. So you need to set these types. And then if you are happy with the SI units that are auto-assigned, which is the case in this situation here, then that is fine. But it's always, again, the manual check. That's what we do right now. Can it open? Is it all as we expected? That seems to be the case. Cool. So now we have in this data folder, we have now our 5 input files. This was our template dummy, and these are the 5 for our scenarios. And I think in the ICZM model folder, there's also a data folder where all these DFS0 files are generated for all the different scenarios, right? So back to our script. Now we need to make the setup files. And now we need to, I run it to here. Again, I have the template, I loop the cases, I open the PFS file. Now I just run it to here. And now HD is this section. And then HD wind forcing. Here's also the auto completion, as you can see. I get to the wind forcing. And then in the wind forcing, there's a file name. So HD wind forcing dot file name. So right now it's pointing to the dummy, right? It's pointing to the template 0. And this guy we need to point now to the case. Now I kept it quite simple, my file name convention, etc. So here you can either assign a file name directly, But since the only thing I changed was that I changed the 0 to the case ID. And that's, by the way, where maybe an example where that shows that not too complicated file names can help when setting up these things. I can simply say that in my file name that I have in my PFS template, I want to replace the 0.dfs0 with the row case number.dfs0. So what happens? Yeah, then I want to replace it with this file name. So what I'm basically doing is that I replace the file name and then I save the output. So I put it back together. Batch, we have only the first input file. Now I run it all. And voila. In my batch, I get here my 5 newly created setup files. And then again, the check. I open these two, for example. Plugins, compare. Boom, what has changed? Okay, the only change here in the profile, WinSpeed profile 1, I'm pointing to WinForcing file name data WinSpeed 1. In the WinSpeed profile 3, I'm pointing to WinForcing file name data WinSpeed 3. So I'm happy with that, right? That's what we wanted to do. We wanted to create the DFS0 files, and we wanted to create the setup files. And now I do an additional check that everything is green here, everything is green here. I have the WinSpeed 3 here. That's fine. So that are these quick manual checks. Then again, I make a batch file. By the way, here it shows a little different batch file because it started to make a difference that I added the little minus GPU flag here. When you run a purely HD model, you know that you can run it on the graphical, on your graphic card. So the minus GPU does that in the batch file. So I create the batch file. Now I have this batch file, 5 cases, and I have the minus GPU. Minus X, I wait until it's completed. And then I now could double click this to run all models, or as before, we go to the folder where it is already run. And then we analyze the results. So I now go to the model dir where it's already run just for the presentation. Then I load the results. And this time I take the time series in point 1 and then the profile at the end of the peak. Which is time step 27. I have hard coded this here. You could probably do it in a nicer way to be more flexible. Now I loaded the results. Again, explore. Results case sphere is my time series. I can plot that. It looks like this. Okay. So it follows, it reaches basically the maximum water level also with the peak of the wind speed, and then it falls down again. Results 2 are my profiles. It's at the end of the peak, so it's in here in time, but then across the domain, it looks like that. Nice. Okay, then we can compare it's a bit like before, right? Now we can compare the time series. So these are now the water level at point 1 for the different wind speeds, or the different wind speed peaks, actually. So it goes up, it stays stable, and it falls down again. We can actually also now see from this simple example that the response to the shallow water wind setup is quite immediate. So if you have a wind speed ramp up and then it's here at this plateau. So for the shallow water wind speed setup, it's not so relevant how long your storm event is in your in your model storm profile, right? Because it's here and then it falls down again. And then we extract the water level at the peak from the results. So we can also plot the water level at point 1 at the peak versus wind speed. That are these ones, also 0.11, which is this point here, and then compare the different profiles. That's what we have here. And again, the funny whatever is going on here, right near the coast, in at least this coarse mesh. So that was this example. And the key thing here was now to introduce the generation of DFS0 files and to use these DFS0 files in your simulations and doing that in a programmatic way so you can generate many cases. Any questions on that for now?
في اسئله سمعت من لو فاكر اللي كان المره دي كنا بنعمل جنريت دي اف اس 0 مش يونيفورم مش يونيفورم سبيد وز فايل اوكي وعملنا الرن وعملنا كومبيرنج للريزلتس فهل في اي اسئله مرتبطه بالبيزك؟
في بس في فيجر هو الاكس اكسس بتاعه في بس بالسين وبتبقى بتاع سايد لاين
ده تقصد اول فيجر بتاع الستورم
هو ده
please show us the first storm calculations, the first slides figure
Yes.
for storm calculations.
Yes. So I wouldn't want to call it calculations. It's synthetic storm profiles, right? So we defined that we have a storm profile that starts at 0 wind speed. It starts at 0. It linearly increases over 1 day to a peak value. Then the peak value is kept for 3 hours, and then it decreases again to 0. If you use this representative storm profile or another one, that is also that is an analysis that you need to perform for your local conditions. But it's not exactly the one that was used in the ICZM projects, but it's similar to it. It's like a trapeze profile that was chosen. And what we basically do here is that we define. So the only the only free parameter in the way I did it now is the wind speed at the peak. Everything else is set. So the wind speed at the peak we vary from 0 to 40. And then I just in the first step I just define the point. So for each case I loop over the cases, and then for each case I define this point, and this point, and this point. So 4 points with X and Y, and then I interpolate linearly to a 1 hour time step, and then I end up with these 5 wind profiles. And by the way, I also define the wind direction, because when you choose a mic to have a DFS0 as input, you also need to define a wind direction. But in our case of the simple domain, it's just blowing from west to east, and it's not changing in time.
I would like also to focus on the storm. What I say in the presentation, not in the
Yes.
visual storyboard.
So I guess you mean this.
Yes, this figure exactly. He was talking about the
x-axis.
why the x-axis there are negative time in hours and positive in hours. From where you calculate this figure?
Well, this is now the step of analyzing your data set to figure out your historical your representative storm profile. And here all is done here is in the hindcast you find the largest peaks, and then you normalize your time vector to the occurrence of the peak. So minus is before the peak and plus is after the peak. And that's a normal way of doing it, to be able to plot all these storms in one graph. Because as I said before, this time series that I chose here is arbitrary, right? In in Python or in pandas, I could have also easily defined minus 24 hours, 0 hours, plus 24 hours. But Mike cannot accept a relative time axis. So I need to come up with an arbitrary absolute time axis. But these things didn't happen in January 2024. We all know this. It's an arbitrary time axis. Actually, I like this one better, a relative one, because that's what we're looking at. But we need to deal with the constraints of the model that we're using. So I hope that's clear how there can be negative here.
كنت فهمت ان هو عمل استكشن الايفنتس بيجنس الموجوده والناس بعد كده عملوا
هو عمل
استكشن الايفنتس الموجوده كلها في الستورم
مظبوط وعمل لها بلوت نورماليزد عن الزيرو
وجاب الافرج بتاعها ده الايفنت بتاعه
بالظبط كده وخد افريج يعني خد حاجه سيمبوليك
اسمها بي او مش عارف ايه
ايوه بالظبط حاجه كده بالشكل ده
انا بس عاوز اعرف هو عمل استكشن الايفنتس دي كود معين ولا هو في ازاي يعني هو عمل استكشن
الميثودولوجي بتاع الاكستراكشن
يعني كده بس
one question related to the methodology to